All right. Well, thanks for coming out, everyone. I'd like to introduce our speaker, Jonathan Webster. He's going to be talking about Legendre's conjecture and some numerical calculations that were done towards verification of this conjecture. Um, Thanks for coming.
Yeah, thank you, Michael, for inviting me. It's largely inspired by some of what Michael did on his YouTube channel. About 9 months ago, he gave a talk explaining why we believe Legendre's conjecture to be true. And somewhere in the talk, he mentioned that it had been empirically verified up to about 2 times 10 to the ninth. And he called this a fairly large number. And from my point of view as a computational algorithmic number theorist, that didn't strike me as a fairly large number. So I thought, and my colleague John Sorensen here thought, maybe we can do better, especially if we design an algorithm around that. So I'm going to talk about that. I think about that. So here's an outline of the talk. I'm going to kind of give an introduction. This is a little bit of an overview of who I am and what I do as a mathematician. Explain about how I'm going to think about computations. I'm going to give you an overview of Legendre's conjecture. And if you ever go watch his video, I highly recommend it. I'm going to give a different intuition on why I think Legendre's conjecture is likely to be true, why it's not an unreasonable belief, even though we can't prove it. I'm going to explain the prior work and what the Sieve of Eratosthenes is. It's kind of one of the grandfathers of all algorithms, very early example of computational thinking to help us understand prime numbers and composites. We'll give a brief primer on prime testing. So if you take a course in elementary number theory, you might see some of these tests. So certainly the first major thing for Fermat's little theorem is a classical starting point for a course in number theory. And I'll conclude with our new algorithms and explain how we got to where we go. So Gauss, not Gauss, Galois had this quote in talking about the solution to polynomials, but it's interesting. If I read this and I can't help but think computationally is anytime I see a problem that begs for computation, I want to classify it by the complexity of the computation. And so when I hear Legendre's conjecture and want to verify it, I'm kind of think, how difficult is this? Is this a computationally difficult problem, or is this really easy? And how do I classify it? So I do this because I'm an algorithmic and computational number theorist. So I'm going to give an overview of what I do is I like to compute interesting quantities. So what I'm going to talk about today is we found a prime between n squared and n plus 1 squared for every n less than or equal to 4 times 10 to the 13th. And I should have updated this particular slide. As of 9:30 a.m., it's 4.45 times 10 to the 13th. So the computation is still running. So part of this was we designed an algorithm specifically to solve this problem. And I'll explain as we go. We have a carefully selected prime test along with some limited use of the Sieve of Eratosthenes to accomplish this. And anytime you create a new algorithm, you want to analyze it. So under certain assumptions, there's an algorithm that can find these primes for all n less than capital N. And it runs almost linear in n. There's this multiplicative factor of log n, log n. And it doesn't use a lot of space. And that's a nice property, so that oftentimes there's, in computer science, you might have time-space trade-offs whereby using a large amount of space, you can do something faster. So I don't need a large amount of space. That's a nice property to have, especially when you get to memory issues and slower versus fast memory. So one of the reasons I like this area is oftentimes mathematicians might not know what to conjecture, and so you might collect data. I like the theory, understanding what's practical versus theoretical. I just enjoy it. It's something I encourage any student to do, is spend time playing around, testing examples, seeing what happens. like new knowledge. And I always include this. There are real life applications. If you ask me what they are, though, I think I'll take the NSA route and just say, well, I can't tell you about that. Well, we might discover them later, or you might discover them later. Because and that's the nice thing about mathematics is the results in mathematics often precede real life applications, sometimes by centuries. So I'm sure the real life applications are out there for this problem. But to do this, we need to make some use of elementary computer science. And I need to explain how I'm thinking about a computer. And I'm thinking about it as a random access machine. There's simple operations. I'm going to say take one unit of time. And here I'm thinking about memory access. I'm thinking about basic arithmetic operations, bit operations. And then if I have a function call or subroutines or loops, those are not considered simple and will almost always make me want to do some kind of counting. And we do this to kind of level the playing field. I don't want to have to worry about hardware, operating system, or specific programming language in it. And here, computer scientists, especially at the undergrad level, sometimes resent that this changes it back to a math problem. But as a trained mathematician, I like having a problem and counting. I enjoy that. So we'll see where the counting aspect comes up. Some of the analysis of the algorithm is counting of the algorithm. So to establish this notation, I need it's called Landau notation or Big O notation. And basically, I'm looking for some easily understood mathematical function that provides a bound, an upper bound of my function. And that's exactly how I will often speak about it, an upper bound. The formal notation is this lim sup. If you've not seen a lim sup, strike the word soup and just consider a limit, and you're like 90% the way there. And I think for this talk, you should be 100% the way there. I don't know that I need a lim sup, but I also like things to be correct. So formal definition has a lim sup. And basically, you see a quotient of functions. You're trying to have a probably discrete-like function that describes an algorithm, and a more calculus-style function that bounds the work that your algorithm does. So I'm going to explain Legendre's conjectures. And so in his work in number theory in 1790, I think it's 1798, I tried to trace down the exact year. He conjectured this, but he conjectured there's a prime between any two squares for all n. It should be noted that if I think about these on the real line, the length of an interval he's conjecturing that the primes exist, a prime exists in is length 2n plus 1. And so it's a very common thing. I'm going to try to avoid it, but I'm still not 100% at avoiding it. Is I will speak about things in terms of n, as you've seen me do, but we always deal with numbers of size n squared. So it's sometimes easier to think about this in terms of number of digits. Well, n squared has twice as many digits. So if I'm dealing with things on the size n equals 10 to the 13th, I'm talking about numbers that have like 26 digits. So Legendre in 1798, I know this for certain, also had the following conjecture, that if you want to count the number of primes, that it looks like x over log x. He did this by looking at tables of primes, some early examples of the way computational mathematics can inform theoretical mathematics. And for those of you that might have had a course in number theory, it's not uncommon that you'll see this. You won't see it as a conjecture, though, because it's the prime number theorem. This was proved about a century later independently by Hadamard and Poisson, and they proved this. And this is kind of nice. It gives us a way to think about prime numbers. So we can act like the number of prime numbers is just x over log x. And so, but what would happen if we replaced pi of x with x over log x? Well, some things work and some things don't work. The way you should kind of think about this is kind of the right main term, and there's some lower order terms that you can think of as error terms. So in particular, we're not going to be able to use this theorem to show the existence of primes in short intervals. So in particular, interval size x to the 1/2. The error term on this approximating function is too large to guarantee the existence of a prime in this interval. And I'm going to go back 2 slides. So if you note, this 2n plus 1 is on the order of the square root of this. So this theorem, if you ever see this theorem being used to claim to prove Legendre's conjecture, they're almost always ignoring something about the known error. But I don't really want to, I'm okay from a computational point of view saying, it can be helpful to think about this in a probabilistic kind of way, and I'm just not going to claim that the following is a proof. So if I act like primes are randomly distributed, and I know their relative density, x over log x, I can interpret the prime number theorem as a statement about probability. And then the probability that a random number less than x is prime, I'll just act like is 1 over x. And so if you give me x, I'll say, grab log x numbers, and I would expect that one of those would be prime. It's not this isn't a proof, but if I'm going to be doing lots and lots of computations, it's a reliable way to think about what's a reasonable heuristic to understand how the primes are distributed and how often I expect to have them occur. So the interval from n squared to n plus 1 squared has 2n plus 1 integers in it. So how many of these are primes? Well, by this mode of thought, I can just divide 2n plus 1 by the log of n squared, because that's the relative that's how often I expect to see them. And that's n over log n primes. N over log n is, say in our computational range, say n equals 10 to the 13th, is, well, 3 times 3.4 times 10 to the 11th. That's a large number. So we expect it to be my expectation is it's going to be easy to find 1 prime. I expect there to be lots of primes. And of course, none of this is a proof. I've not proven Legendre's conjecture, but if I'm designing an algorithm, it's safe to say that I'm probably going to stumble across a prime. And the real question is, if this is the expected density of primes in an interval, I should take advantage of that and try to design an algorithm that allows me to pick out primes more quickly than you might naively expect. So let's look at one approach, and it's the Sieve of Eratosthenes. So in 2014, there was this computation that I referenced at the beginning of the talk. They were studying prime gaps, just any gap. And so they needed to find all primes. Finding all primes is kind of too much work, but there's some interesting things about this algorithm. I'm going to write the pseudocode here. Basically, for every integer, you create the possible product, and you mark a 1. So whatever gets marked with a 1, is composite, and whatever is never marked is prime. And so here I'm going to see a picture of the sieve run on the first 900 numbers, a 30 by 30 square. And we cross off composites and we leave primes unmarked. And so it's not too hard to analyze this. You can, the number 2, you have to do 900 over 2, markings off. The number 3, you have to do 900 over 3, marking off, so forth and so on. And at least at Butler, Calculus 2, you see this sum when you study sequences in series, and this is the harmonic sum, and it's not too difficult to see that the harmonic sum grows like log n. And so the runtime of the Sieve of Eratosthenes is a factor of the largest number that appears in it times this log n factor. It's space. You need to store all these things if you're going to mark them off. So this is a large space constraint. And in fact, this is unacceptable for our problem. It's too much space, too much time, and in particular, it's too many primes are found. We only need to find one prime. So our goal was to, knowing this was the prior work, which as I said, was not aimed at solving Legendre's conjecture, we wanted to see, excuse me, we wanted to see if we could design an algorithm that just resolves Legendre's conjecture, just finds one prime and then moves on. But there's some interesting things about the Sieve of Eratosthenes that we don't want to forget. So it has a great average cost per prime. So if you think about it, let me go back one slide. This n squared, it's essentially saying you pay a log n factor. You need to know n squared things and you're paying a log n factor. Well, that's not a large price to pay per thing. It's just it finds too many things. But the average cost is something to keep in mind. The other thing is it turns out the sieve works well in arithmetic progressions. So if you have a sequence that always differs by the same multiple, you can apply the sieve to this sequence. I'm going to go back and show you a quick picture. And you could think of that in this picture by sieving by column. In particular, I really like this column, the first column, the things that are one more than a multiple of 30. You can go down here and do this. And I think 91 is the interesting one. 91 is 7 times 13. And if you look, 1, 2, 3, 4, 5, 6, 7. 301 is a multiple of 7. 1, 2, 3, 4, 6, 7. 511 is a multiple of 7. And so you can apply the same principles of the sieve, go down and mark off in an arithmetic progression. So that's it's an important feature to keep in mind. And the other nice thing to know is that it doesn't, if you don't run the sieve to completion, you don't choose every prime less than the square root, the things that have marked off, you still know for certain are composite. And so you might, you can use this to kind of think about and this is where the sieve comes from. You can think about an incomplete sieve, what's left in your basket are things that are prime and things that are products of larger primes. And from a computational point of view, just eliminating some of the obvious composites is a huge advantage. Like going back to the random model, where I think about grabbing a random number and saying, is this prime? And I have to grab log x of them before Cramér's model tells me I have a prime. Well, maybe I shouldn't grab even numbers. Maybe I could avoid grabbing multiples of 3 and construct an m here so that I'm more likely to be grabbing numbers that are going to be prime than not. And so if you redo the analysis, I'm not going to certainly not going to do this talk, you'll see that there's really two major things is how far you sieve and the interval length you sieve. And you typically will just have these matched. Whatever the length is, the number of numbers you store, you're just going to sieve by the primes less than the length of your sieve. But you can always go further and just maybe do empty work. Let's talk a little bit about prime testing. This was a huge goal in modern algorithmic number theory, was to kind of solve this problem of Gauss definitively. And he wants to know, like, how do you distinguish composites from primes? Like early in a mathematical training, the difference between determining primality and factoring, it's not clear that there is a difference. It turns out that these are wildly different complexity. We think these are wildly different wildly different complexity problems, that factoring is much harder, and that you can detect primality without actually finding factors. And so here's an example, Fermat's little theorem. Fermat's little theorem says if an odd integer p is prime, then a to the p minus 1 is congruent to 1 mod p. Now, if you've had number theory, you'll know exactly what this means. If you haven't had number theory, I'm just going to tell you what this means is if you do a computation, an easy computation, you'll get the result 1. And from a computational point of view, I tend to think of Fermat's little theorem not in this form, but in its contrapositive, which is to say, if I do an easy computation and the result is not 1, I have seen that this number is composite. And so it might be weird to have this on this page about prime testing because this is really a compositeness test. And so there's this big, you can have some portions of a number theory class might address modifications to Fermat's little theorem to kind of start recovering it to be a prime test and not a compositeness test. And it turns out that there are certain numbers that, stated in this form, you'll never detect as composite. So it's not just that we can't prove it, there is an intrinsic failing in Fermat's little theorem. So this was the goal, like in the 1970s, it was pretty clear there should be a prime testing algorithm that has these 4 properties. It's general, it's deterministic, it has a kind of what I'd say is a fast runtime, and is proven unconditionally. Up until about 2002, 3 of these 4 could be done. Just pick your favorite 3 and do this. And even today, if you kind of dig into the roots of the prime testing in your computer, where it's done for cryptography purposes, usually you're giving up at least 1, maybe even 2 of these for the prime testing used. So sometimes they don't care about deterministic, and they don't care that it's an unconditional proof. They just want a fast general algorithm that we will likely believe is true. But this was finally resolved in 2002 by using a polynomial version of Fermat's little theorem that says if you compute the left-hand side, do a computation on the left-hand side, and you get the right-hand side, well, now you have a biconditional. And the issue was that the authors needed a very clever way to avoid the full expansion of this. So I don't want to go into it, but they found this clever way. It's due to Agrawal fixing it. Oh man, now I feel bad. I'm blinking in my hot seat. AKS. They found an algorithmic interpretation of the above, and they gave this an algorithm that runs in log n to the 12th time to unconditional, general, improve primality of anything. And a few years later, inspired by their results, Pomerantz and Legendre changed some of the underlying structure, but still it's fundamentally still an algorithmic interpretation of this congruence, and was able to lower 6 down to a 12 in their proof. It could run faster. I mean, that's possible, but this is what we're able to prove. But leading up to this, there was all kinds of other modifications, and I want to talk about a special prime test that was developed over several years, some that came before AKS. And this had its origins in Edward Lucas and Lucas sequences. Pocklington had a role in this, but the version I state here is due to Brilhart, Lamer, and Selfridge, the BLS. So basically, it still looks a lot like Fermat's little theorem. You kind of see Fermat's little theorem here. The a to the n minus 1 is congruent to 1 mod n. That looks like a test for Fermat's little theorem. But the idea here is if we can factor this exponent, We can factor the exponent. Well, knowing what the prime factors of n minus 1 are was the insight of Lucas and Pocklington. Then you can remove those prime factors and test this GCD, which is also a fairly fast computation. And if this GCD holds, then it becomes a primality test and not a compositeness test of the Mossler theorem. I think it was Pocklington had a 1/2 here. Brilhart, Lamer, and Selfridge showed that if this factored part exceeds 1/3, then you do a slightly additional test where you check that this quantity in the base F representation of n minus 1, that the coefficients don't give a square. Again, that's still a very fast computation. So from a computational point of view, I see a fast computation, a fast computation, fast computation. It gives a primality test. So this is one of the earlier attempts to recover from Moss's theorem into a prime test. It has the which is really nice, but it has the kind of unfortunate property that this fast primality test now depends on factoring, which can be painfully slow. And so one of the initial goals was how small of a factored part can you get, which was the motivating reason for lowering this 1/3 bound. And this test is for me very interesting. And it's the one we ended up relying on. So what's the initial attempt if somebody says find primes? Well, you just start at the left side of the interval and move your way forward until you find a prime. The expected cost is the expected number of tests that you're going to do. How far in this interval do you need to go, times the cost of your primality test. So if I use a naive version of the analysis of the AKS algorithm, Cramér's model says I have essentially log n things I need to check before I find my prime. And then the cost of each thing is a log to the 12. But then I need a sum. I need a sum for every n less than capital N. And so then, well, that's n times log n to the 13th. This is very unrealistic. There's no claim that anybody here would implement this algorithm, but it does have the property that it's unconditional, it's general. It's not that bad. I mean, it's better than quadratic. So we should improve this. My colleague John Sorensen has done work on something called a pseudo-squares prime test, and with a certain pre-computation that's been done in our computational range, you can actually change this 13 to a 4 if you use a pseudo-squares prime test. So that's a huge improvement. It does rely on a pre-computation that fortunately well exceeds any future work we intend to do. So that's fine, but from a algorithm analysis point of view, maybe we don't want to rely on a prime test that requires a pre-computation. It does have the benefit that there's almost no space storage. Big O1, I mean, you don't need to store all of these numbers. You can look at one number, check it. If it fails, create the increment and move on. So it has a very low space requirement. And we like that. Makes it memory efficient. So that factor of the capital N, there's really no way you're going to avoid that. So then the real question is how small of a multiplicative factor is possible. So go back. So here I have a multiplicative factor of log n to the 4th, and I'm trying to think of how do I reduce that? Well, so some of the early insights we had was sieving is very helpful here because it works well in arithmetic progressions. So if we design an arithmetic progression that allows us to find primes more easily, that could help reduce the expected cost. This will impose some kind of space requirement. We're going to have to store things if we want to run a sieve. So our goal is then to be careful about our sieve. We don't want the problem to become infeasible due to memory requirement. But the reason I chose the Brilhart-Lamer-Selfridge test was precisely because this works when a large prime factor of n-1 is known, and a sieve works well in arithmetic progressions. So I can design my arithmetic progressions so that n-1 has a large prime factor. So do that. We'll let R be large enough. Let R exceed into the 2/3. And you might think back to the Brilhart-Lamer-Selfridge test, and you say, didn't you have a 1/3 there? I did, but remember our bounds are the numbers are of size n squared. So this is n squared times a third, so that my factor is large enough. And then we're going to look in an arithmetic progression of the form 1 plus some multiple of this prime. Now, when I subtract 1 from this, I'm staring at a number that has a large prime factor, and I know it because I found it. And so the candidate will have the correct property for the Brilhart-Lamer-Selfridge test, which is essentially the biggest expense you incur is the modular exponentiation, and that is 1 factor of log n. So then how much space do we need so that the sieve, if I start forming these arithmetic progressions, how much space do we need? Well, Cramér's model suggests we need at least log n candidates per interval we want to verify Legendre's conjecture on. So I'm going to do the rest with kind of finish with an example. So let's look at something that's somewhat meaningful, close to our computational range, and say, let's look at this interval that I started with before. This interval that the first interval had, we believe would have like 10 to the 11th primes in it. And I want to carefully design an arithmetic progression so that picking out the some prime in this interval, I'm highly likely to find to be successful in relatively few attempts of invoking a prime test. So this particular problem says, so what we're going to do is not verify it for 1 interval. We've got 30 intervals here. So here's a prime. This is easily computed. In fact, for writing the talk, I just asked the Magma online calculator, what's the next prime after this number here to the 1/3, and it gave me this number, whatever this is, 464,158,907. Yeah. And so now I need to start thinking about the arithmetic progressions. So the arithmetic progression needs to have at least this log of 10 to the 26th, which is about 60 candidates per interval. So I want to overshoot a little bit because I don't want to re-invoke this. I don't want to invoke this algorithm in case we miss. And that's part of the probability here is, since I'm relying on kind of dice, you might think of it as dice rolling, while I do expect it to occur in 60, I'd rather play it safe and not have to do this, pay the setup cost again and try an entire batch of 30 intervals just because the first interval failed. So we round this up to 128, just round it up so that we're unlikely to miss a prime. I think in the actual computation, it's even closer to in the 200s. So that we, yeah. But now R itself is too small. So what we want to do is choose a multiplier to stick with R so that the size of m times R times the number of candidates I want to check is roughly the size of the interval. And then we'll sieve. We'll go in an arithmetic progression of this constructed product and check in that arithmetic progression. So it turns out that the numbers work out that I choose you choose consecutive prime numbers, and here I can fit 2, 3, 5, and 7. And then you still want to choose some kind of scaling factor. If you can fit 11 in, you'll do that. I can't fit 11 in, so I fit 2. 2 happens to work, and so I pick m is 420. And then across the 30 intervals, there's about 3,176 candidates to check in total. So I kind of undershot a little bit. That's on average about 100 candidates per interval, but still well over 60. And so we construct candidates in the arithmetic progression 1 plus k times r, where r is that prime I mentioned before. And one nice thing about this particular number is that by adding 1 to its multiples, we from the get-go, before we do anything, I've already guaranteed that no number is a multiple of 2, no number is a multiple of 3, no number is a multiple of 5, and no number is a multiple of 7. So I'm essentially, all I need to do is then sieve. The next prime I'll look at is 11. So I'll go through my 3,076 candidates and mark off every 11th one once I figure out the correct starting place. Then I'll go through and mark off every 13th one once I figure out the correct starting place. And I'll do that for all, I do that in all 30 of them in one go, all 30 intervals in one go. And then after I've completed sieving, then you go back and start checking what's left and do prime testing on what's left. So it turns out that the first interval has 101 candidates in it. And then I checked sieving, so removing everything that has a prime less than 3,076 removes 69 of them. So there's 32 candidates left that are either prime or a product of some number of primes where the primes are all greater. The least prime factor is greater than 3,076. Turns out that if you repeat my work here, the fifth number not removed by sieving happens to be prime. So in this example, there were 4 failures. There were 4 numbers that were composite, that had least prime factor exceeding 3,076 that were composite, and it was the 5th number. And there's the 5th number. But upon finding this 5th number, the 5th number is prime, it's relatively easy to move. Then you've now verified it for the first of 30 intervals, and so you compute what the next k value is that will start that represents the starting point of the second interval, and then you kind of jump ahead and start checking that interval, and hopefully you don't find you go 2 or 3. I didn't finish the example in that regard. Check as many as you need, and you're highly likely to find a prime very quickly. So the certain assumptions. Well, what's the assumption? Well, the assumption is Cramér's model. In order to say anything meaningful, you have to assume something way stronger than even Legendre's conjecture. So this is it's a theorem, but the theorem is conditioned on a heuristic, and the heuristic is that the probabilistic model regarding the prime number theorem it determines how fast our algorithm. Of course, we say it's an algorithm to verify it. If the conjecture is false, well, then we'll never verify it. So that's kind of implicit in all of this. So it can find these primes, the n log n log log n time, and a space. This is not a very large space to pay. The log n is the price of the primality test. So that was the singular modular exponentiation, and the log n you can think of as balancing the work of the sieve against the reduction in the expected cost. Like how many attempts do we have to get before we find a prime? The probabilistic model says that we will expect to have some failures. We just don't want the function that describes that failure to be too large. So we can do this in expected time log n. And of course, once you know how far you have to sieve to bring that cost down and balance things, that tells you the space constraint. So what we've done as of this morning, we've checked all of this. The batches that we do are actually of 131,000 candidates at a time, and we dynamically choose the number of candidates per interval based off of this in our modulus. So it's a little different than how I presented it. How I presented it, it seemed as if the 30 intervals were preset. It's the number of things we check is preset, and then we design our parameters to fit this space. And cache is a big thing. It's common relatively early in a computer science curriculum that you might learn about memory hierarchy, and sieving is not something that does well in random access memory. We want this to be in cache, and so we don't want this to be too big, or else we'll be having cache misses. So this is chosen to easily fit in cache. There's nice C++ libraries that allow the bit manipulation of just flipping a bit on and off, and we use their bitset class. The modular exponentiation, we tried to write our own, but we couldn't beat GMP's. This is GNU's multi-precision library for the modular exponentiation. So one of the first things we do is when we have a candidate, we convert it to the MPZ type and use GMP's modular exponentiation for the Brilhart-Lamer Selfridge tests. The sieving does exceptionally good work at thinning out our set. On average, we're only testing 2 candidates per interval to find a prime. So it's very good at weeding out composites and not allow and removing a lot of the failed costly prime tests. Right now, we've been running it, I think, about 9 months. That might be an overestimate. I think we started, yeah, maybe it's only 6 months. Anyway, the primary run has been on 4 Xeon Phi processors. Each Xeon Phi processor has about 64 processors, so 256 total processors. Recently, we moved it over to a computer that has 192 Xeon cores, and it's been running on that. And yeah, so that's the results. Thank you for your time. I appreciate everyone that showed up. Do you have any questions?
Okay.
Hi, thank you for your talk. I have 2 questions if that's okay.
Sure.
So my first question is it's actually about the number of primes in each of these intervals.
Yeah.
So has anyone looked and seen, I guess, like, you know, computed if you look at the actual number of primes in each of these intervals, does it agree, or like roughly is it the same as the heuristic you get from the prime number theorem? Has anyone looked into this?
So I believe the answer is yes. Let me go way back. Let's see if I can get there. But here I'm a little rough because I'm not as familiar with this work from 2014 when they were studying just arbitrary prime gaps. But I think the idea is that in the aggregate, because the prime number theorem is telling us something about like how primes are distributed in mass, the answer kind of intuitively has to be, yes, this is how they're going to be distributed. We just don't know that they are always distributed this way for every n. You could have a large prime gap. That could happen, but it can't happen all the time, or else the prime number theorem would be false. And the other issue is so this computation found every prime. So but when I'm talking about my computation where I say oops, where do I can I give this estimate? Oh, here, I say I would estimate this many primes in this one interval. Well, I have no clue. This could be a fluke interval that I've chosen that has an asymptotically fewer number, just this one time, and I'd have no clue. And the cost to find all the primes even in this one interval would almost exceeds the entire cost of the computation I've already done, because it's an interval of length 10 to the 13th, and the sieve takes time linear in your interval length. I don't have that time or space to computationally verify that this is anywhere close to being correct. It's just it's a heuristic. I believe. I could be wrong. And that goes for any of these intervals, or the next one too. I think that's how many there are, but the model under the prime number theorem uses doesn't give me the precision to say this is correct.
And thank you. My second question is and maybe you or Michael will know about this, but are there any partial results for Legendre's conjecture? So I guess like one thing I wonder is like, okay, maybe you can't it's hard to prove Legendre's conjecture for all n, but maybe you can prove a statement like of the form like, okay, there are infinitely many n such that Legendre's infinitely many instances of this.
Oh, so I think the idea is if you change the, let me go back up one. I know that it's a theorem if you change the 2 to a 3. That's a theorem.
Oh, okay.
And beyond that, I don't know. I think it was on this slide somewhere, maybe it was the next slide, where I said this. This is in essence the Riemann hypothesis. Would tell us intervals of this size. Actually, the Riemann hypothesis doesn't even tell us this strong. So we're talking about some major significant results in number theory that don't even imply the strength of Legendre's conjecture. But yeah, but I mean, the model I'm using implies something way stronger. It implies like a gap of size log squared, and there's reasons to believe that heuristic is wrong, just outright wrong. But from a algorithmic and computational point of view, it's the underlying thought, and it has served us well, and the timing information bears out. And it could just be that because on average it is right, and that the place that it's wrong is way outside of our computational domain.
Thanks for coming out again.
Yeah, it's my pleasure. It was a lot of fun.